Hello everyone, welcome to week 5 of 2110. I'm going to be giving the Fabrication and Mechanism Design lecture today. My name's Anna, I'm the instructor for section A10 this semester, and I've been a head TA and a GTA for the past year for this course, so I've used some of my experiences to put together this lecture to help you be successful. So the first thing I want to do is go over my objectives for what you'll learn from this lecture. The first one is to understand how and why you should use CAD before and during the conceptual design and prototyping phase of the project. Talk about how to do proper material selection for your machines, comprehend the joining and fastening methods that you can use, and also just some general fabrication tips that I've picked up. And then finally, review how to avoid common mistakes based on lessons learned from past semesters. So, one of the tricky things about ME 2110 is that it is practical design, which means that your project can be very time-consuming due to the fact that part of your grade relies on your ideas actually working. So not only do you need to have good ideas, but you also need to have good construction to make everything work as it should. It's also important to remember that your construction needs to be feasible with the tools that are available and also the skill sets of your group. So you can, once you get put in your groups for the final project, you can choose what tools and manufacturing methods are going to be most appropriate for you to use. And then obviously your construction needs to be done well. Here is one overview of the design process from the Chicago Architecture Center. I like this one because it has 6 steps and we can pretty easily map each one to part of the 2110 curriculum. So the first one is define the problem. In 2110, we use design tools like the House of Quality, specification sheet, and function tree to define the problem. Step 2 should kind of be happening concurrently with step 1. It's collect information. So most of your information for this final design project is, of course, going to come from the final competition document that you're going to be provided soon. You'll use that to fill out your design tools. Up next is brainstorm and analyze ideas. That's when the rest of your design tools come in. So the morphological chart is a great brainstorming tool if you use that. But you can use other methods as well. You just need to use the morph chart in your reports. And then once you have some good ideas put together with your morphological chart, you'll use a selection matrix to analyze your ideas quantitatively. So after you've chosen one idea, you're going to move on to step 4, which is to develop solutions or build a model. So when you're developing your solution, that's really going to be where you're getting into your CAD. Once you've done your CAD, you can make your physical prototype and then start testing it. Step 5 is to present your ideas to others for feedback. So that is going to be the design discussion you have in your studio, the reports you turn in to your instructor will give you feedback, and then the sprint phases of the design competition are great times to get feedback. And that'll lead you to step 6, which is to improve your design. Iterative design is very important. You always want to be improving based on the feedback you get from the instructor, your performance in the design sprints. And as you can see, there's kind of an order to this design process. There's a flow shown by the big arrows, but there's also those smaller dotted arrows that show that you should be moving back and forth between them as necessary. So if you get pretty far into your CAD, for example, and realize that the design isn't as feasible as you thought, you might want to move back to your morphological chart and see what you should do differently. So I want to focus in on what I think was one of the more important parts of that is overlooked a little bit sometimes, which is CAD and how that relates to doing conceptual design. So here are some of the reasons that you should use CAD and how it's going to be helpful to you. A big one is that it helps you locate and orient your subsystems and parts. So it lets you decide where things are going to be placed without actually having to make them and fiddle with them in person. It lets you visualize it very well. It lets you generate concepts very quickly. Pretty much instead of having to remake or rebuild something every time you want to change something, you can just copy the old parts out of your previous concept, change what you need to, and then you have a new design a lot easier than making a new one from scratch. It's good for this class because you can easily share your files, so you can cooperate and communicate with your team very easily. Once you've made a conceptual model with maybe some kind of like rough geometry of the different components of your robot, it's really easy to move into detailed design. So for example, you can add in your mounting holes or smaller details that aren't as important to conceptual design, but you of course need to do before you actually start making it. It's also pretty easy to evaluate your CAD models with engineering tools like FEA. SolidWorks has a built-in simulator, so you can check if, for example, a wooden robot arm is going to break if you put something heavy on the end of it. And then finally, CAD is very necessary for using the rapid prototyping processes that we use in the Invention Studio and Idea Lab. You need to have a complete STL file or an Inkscape file before you can actually use the laser cutter or the 3D printers. There are some drawbacks to CAD that we're going to acknowledge. So it does take away some of the upfront hands-on experience that you get with just tinkering with different fasteners and different materials. It can be a little bit difficult sometimes to ensure that your concepts are physically able to be manufactured or put together in the real world. So sometimes this isn't as much of a concern with additive manufacturing with 3D printers. Most things are going to be manufacturable with that, but it could be hard to assemble something that has a lot of internal features, for example. And then you can't test certain effects without making some assumptions. So if you do decide to use the simulation tool in SolidWorks, it's going to be hard for you to, say, put in exact friction values for a material. So things might end up not as you would expect in the real world versus in CAD. So you do need to balance doing some physical testing versus doing it in CAD. So when you're using CAD in conjunction with prototyping, there's a definite trade-off involving time and effort. So do you want to put more of your time and effort into designing upfront in CAD, or do you want to put it into building and tinkering? Generally, the answer for this is put your effort into designing upfront and doing CAD. Here's an example case study. It's an end effector for an electric sander. So in this, the creator spent about 15 hours on CAD for all of these parts here. It took about 3 hours for them to manufacture using a water jet, and then it took them only 15 minutes to put together. So if you had chosen to make that, maybe with traditional manufacturing methods with very little CAD, of course you'd have less CAD time, much more manufacturing time, and then much more assembly time, trying to put everything together and pick out the right fasteners as you go. I have a couple of tips for you when you do your CAD. There's no need to go through and model every single part from scratch. If you go to McMaster Car, which you can buy some parts from if you want to, they have quick shipping, although it's a little more expensive than buying from Home Depot. Most of their standard parts actually provide 3D SolidWorks models. So if you go to the product detail page for any part, you can request the CAD model in any file, in most of the common file formats. And then you choose 3D SolidWorks, hit save, and then you have a model of a drawer slide. They have nuts and bolts, anything you can think of. If you're looking for some inspiration or possibly more complex parts, you can also check Thingiverse and GrabCAD, which are good free websites. The next thing I'm going to do is go over the manufacturing methods that you have available to you in ME 2110. You're probably familiar with these from training, but I'm going to go over a little bit of how to use them to your best advantage in this class. The first one is the laser cutter. Of course, you use it for two-dimensional cuts, often wood. We're going to use 1/4 inch wood generally in this class, but it can go up to 1/2 inch with the right settings. Although it's usually used for wood, it can also cut some plastics. Another thing you consider is using the water jet if you need to cut through thicker material or any other type of plastic or metal. But it can kind of turn a lot of kinds of wood into a pulp, so you need to be careful with that. But there is a water jet in the Invention Studio. The laser cutter is most appropriate for if you're cutting curves or very complex geometry. If you need very high precision and repeatability, so if you're trying to put holes for screws or bolts in a particular place, it's great for that. It's also excellent for gears in this class. It is less appropriate for if you're just cutting a straight edge. Sometimes it might be quicker to just use the bandsaw or a jigsaw instead. That's if you so you don't have to worry about making the reservation for the laser cutter online and going in and doing all that just for one simple component. It doesn't work for most plastics. It can release noxious fumes. And then it doesn't work on thick materials either. It can't burn all the way through. Here are some examples of things that you can make using a laser cutter. So on the top left, it shows some gears. I love using the laser cutter for gears because it cuts them out so quickly that you can try a bunch of different designs and gear ratios. It's really easy to experiment. If you're having a problem with your teeth not meshing, it's not a huge deal. You can just cut out another one in another couple of minutes. Below that is sort of an interesting idea for turning your 2D laser cut into 3D. They cut out a hinge in the wood. And then over to the right is a full assembly. It looks like a quadcopter that someone made the full structure out of laser cut wood. So that's just an example of what an assembly could look like. And like I said before, gears, great for laser cutting. SolidWorks comes with a gear toolbox. It's a good resource to use. You can kind of just decide what your gear ratio is and it'll generate them for you. And the gear teeth shape it uses is very good. They always mesh. I've never had a problem. There are also some gear generator websites that you can use. It can calculate the pitch diameter, number of teeth, gear ratios, all those good things for you. So there's a couple of links right there. This will be posted on the website, so you can check those out if you want to. So since laser cutting does only work in 2D, you are often going to find yourself needing to move a design from 2D to 3D. And a way to do that is with something called finger joints. You can also use hardware or glue. But a finger joint is what's shown in the black and white picture up at the top. It's pretty much just the pieces of wood have fingers cut out on the end, they interlock and stay together. And then the bigger picture that's red and blue shows how you can use a finger joint in conjunction with hardware to make it super strong. When you are designing a finger joint, a good rule of thumb for how wide it is that it should typically be as wide as the thickness of the material. So each finger in the joint should be pretty much a cube. It's a good rule of thumb. Something that we haven't talked about yet is laser kerf, and the laser kerf is how much of the material is actually burnt off by the laser and lost. That gives you a lot of clearance if you're designing something that is going to be interlocked. So because of that, if you're designing finger joints, you can actually make all of the parts that interlock the same size. And then the laser kerf will give you a little bit of extra space and they'll interlock pretty nicely. The next piece of equipment that you have available for your use is the 3D printer. So the Idealab 3D printers are Ultimaker 2 pluses. They use fused deposition modeling, FDM, with PLA filament. And it works by printing STL files exported from CAD programs, which you learned how to do in the past couple of weeks. So here are some examples of things that you can do with 3D printing. 3D printing is great for making new parts to interface with existing parts you have. So for example, motor mounts, motor couplings, bushings, which of course is great for this class because you're given a bunch of mechatronics components and you need to interface them together. It's good for making parts with complex 3D geometry, and it also has the very cool feature of being able to make assemblies that are interlinked. 3D printing is not so appropriate for making 2D objects. For example, gears. A lot of people will use 3D printing to make gears for this class, and not only are they a little bit weaker, but they also take a really, really long time to make, so it's just not the most appropriate manufacturing method for this. And we've also seen people make boxes or other items, and if you're trying to make something like a box, you should always think, can this be made more easily by just making a bunch of 2D parts and then assembling them later after the fact? Here's an example of a good use of printing for ME2110. So this is from last year's competition. All of those parts you see in orange are 3D printed. And this is a good candidate for 3D printing because they're totally custom parts. The geometry is three-dimensional and very complex, and it also interfaces with the mechatronics components. So this is a gripper that holds and releases a little sphere, and it uses the solenoid to open and close the gripper. And here's another example of why you should not 3D print a box. A lot of times 3D printing can end up warped, it's very slow, whereas laser cutting is always flat because your material is flat. It's very, very fast, and it's more accurate. So up next, I'm going to go over some of the materials that you'll have to use and that I would recommend for you to use in your projects. So up first, of course, the big one is wood. So if you go to Home Depot, you'll see natural wood, which is pretty much your lumber, comes off a tree. Hardwoods and softwoods are the two different types. Hardwoods are more stable and less likely to warp than a softwood. So like a hardwood would be oak and a softwood would be pine, for example. The big con to this is that they're very expensive. So if you weren't working on such a tight budget for this class, I would definitely recommend using natural wood. But since you do have a budget for your robot, I recommend using man-made wood products. They're very cheap, and the two most popular ones are MDF and plywood. So MDF stands for medium density fiberboard. It's what you used in your fabrication training to make the side panels and platforms. So pretty much it's just wood all chopped up really small into fibers and then compressed very tightly with adhesive. So it's kind of just like really, really dense cardboard is how I think of it. That is a great choice. It's super, super cheap. But like I said, it's made of a bunch of fibers that are compressed, which means it can be pretty easy to tear the material apart, especially with a screw or a drill. So if you are using screws and other types of hardware in MDF, it's very important that you use pilot holes before you drill into it so you can keep the material from tearing itself apart. Then the other one that I mentioned is plywood, which is the picture in the bottom corner, also sometimes called OSB, which is the particular type that's shown. You shouldn't laser cut this because it's just thin sheets of wood glued together and the glue can catch on fire. But if you're not planning to laser cut, this is also very inexpensive and a good option. Another type of material you might consider are plastics. So oftentimes people will use PVC rods or pipes in this class. Those are great because they're inexpensive. You can buy them in 10-foot increments for just a few dollars. And they're also very easy to work with. You can cut them even by hand with a handsaw. There's also HDPE, which we used to use in ME2110 to make motor couplings. It often comes as flat sheets or a round stock. It's very easy to work with. Is a very low friction surface, so that was why we would use it for motor couplings and bearings. So in ME2110, plastics are very important to be used for linear or rotational bearing surfaces. So what I have shown in the top picture is a traditional metal ball bearing versus a plastic sleeve bearing. So you could spend a lot of money on ball bearings for your robot, for the ends of your shafts and axles, or you could just have what is pretty much a tube of plastic. Plastic has a very low coefficient of friction against most other materials, so if you have a metal shaft sitting in that plastic sleeve bushing, that is totally fine for the applications we need. You don't need anything fancy like a metal ball bearing. Plastic on plastic has a very good coefficient of friction against each other. That would be the ideal setup for a sliding surface or rotational. And then the last one is metal, of course. Metal is most appropriate if you're making something that requires a long lifetime or that's going to be undergoing a lot of wear. You can use the water jet to cut sheet metal to shape if you do choose to use that. Sometimes that metal might come up in 2110 would be aluminum rods for shafts or 80-20 extrusions for structure. However, metal is definitely more expensive than wood, and there also aren't any metalworking tools in the Idea Lab, so you would have to work in the machining mall or in the invention studio. But it's good to be aware that these options exist. Alright, so once you've picked out your materials and your manufacturing methods, you've made your parts, you need to join them together. Here are a couple common methods of joining. The first one is nails. That's the top picture over to the right. Nails are great in shear. So if you have two pieces of wood that are going to be pushed against each other in shear or slid against each other, the nail will be great for keeping them together. But if you're trying to pull those two pieces of wood apart, the nail really isn't going to do anything for you because it has no hold on the material. It's not biting into anything. On the other hand, a screw is great. It draws two pieces of wood together So it's really good to keep a piece of wood that's together that's being held in tension. If the material is under shear, you may see the screw snap, although it's probably unlikely for the forces that you'll be experiencing in this class. There's also nuts and bolts. So bolts are similar to screws in that they draw two pieces together, but instead of drilling part way through the second piece of material and having it nested like a screw, when you use a nut and bolt, you want to drill an oversized clearance hole through both pieces of the material, and then you'll fasten the nut and bolt. This allows you to disassemble and reassemble pretty much as many times as you want, whereas the screw probably only has a certain lifetime before it stops biting into the wood threads. The next one is glue. There's a few different types of glue available that you might use. I'll talk about those later. And then finally, soldering is of course a way to join that you may have experienced during mechatronics training. This is important for making sure your electrical connections are stable. So the first thing I want to talk about is screws. The ones that you are being given to put together your robot and that you'll see at the store a lot of time have countersink heads, which is what's shown in the picture. So if you're working in the Idea Lab, you may need to ask for a countersink bit, so you can countersink the top of the hole so the top of the screw will actually sit flush with the material. And when you're using a screw, you always need to drill a pilot hole before you put it in. So in this example, you can see the two pieces of wood that you're trying to join together. The top piece of wood is going to have a clearance hole, so you can stick the screw through a clearance hole and it'll slide freely. The bottom should be the pilot hole. The pilot hole is going to be undersized instead of clearance hole, and that allows you, when you are screwing the screw in with the drill, there's enough room that the screw can go in fairly easily. It's not going to break or anything, but there's still plenty of material left for the threads to bite into. If you were drilling in, say, 4 screws in a row next to each other like this, you wouldn't want to drill 4 pilot holes and then put 4 screws in. You're going to want to drill your pilot hole, put your screw in, and then do the next one, and so on. And this is so if you end up with any misalignment, which you probably will, then by the time you get to the 4th screw, it'll still be able to fit in. The next one that I mentioned earlier was nuts and bolts. Just like the screw, they hold 2 pieces together, and you need to drill a clearance hole through both materials, which is what's shown in the colorful picture there. You can Google clearance hole for English threads, and then all kinds of charts will come up where you just find the type of bolt you have, and it'll tell you what size hole to drill. You do need to remember, if you're considering using nuts and bolts, that if you have a standard hex bolt, you're going to need 2 separate wrenches to tighten it, one for the head of the bolt and then one for the nut. So if you're working at home, you may not have that accessible to you, so that's something to keep in mind. And then if your nuts and bolts are going to be undergoing a lot of stress, potentially, you may want to be able to lock it. So there are some common locking mechanisms. The main 2 are nylock nuts and lock washers. Both of those should definitely still be used with a regular flat washer. The first one, nylock nuts, is the picture to the left. It's pretty much just a regular hex nut, but at the top there's a ring of nylon plastic. And what that does is the threads bite into the plastic once the nut is tightened so that you can't untighten it by hand. There's a lot of friction in that area with the plastic, so it's pretty hard to get off. And then the other one is a lock washer. You'll hear it called maybe a split washer as well. It's what's in the picture with the green arrow pointing to it. And it's kind of a regular washer, but cut and then deformed a little bit so that the edges of it are pointy, and it'll bite into the material once the nut is tightened down, and it'll resist being turned the other way to loosen it. Right, back to glues. So there are 3 big kinds of glue you might use in this class. The first is wood glue. Of course, glues wood together. It's actually stronger than using screws, and that's because when you use glue to glue 2 materials together, you're putting glue on the entire surface area of both of them. So the entire surface is actually being adhered together, whereas if you have a screw, your materials are really only being held together at the points where the screws are. A disadvantage of wood glue is that it needs to cure and dry overnight. It needs to be clamped while you do this so it doesn't expand. It can get pretty messy and it's also permanent. So with screws, you can always take them out and redo your project, but with wood glue, there's really no taking it apart once it's on. Hot glue, I want to discourage hot glue as a permanent fastening method, but it's great for just some temporary fastening. If you're kind of experimenting with your prototype, you're not sure where you want the final location of a component to be, hot glue is a pretty good way to keep it there temporarily. Once you finalize your design, you're going to want to take it apart and use a more permanent method and a more aesthetically pleasing method, but this is okay for testing. And then finally, epoxy is great for using on 3D prints or other plastics. Please do not use epoxy or hot glue, really any kind of glue, to be mounting or coupling mechatronics components. You need to turn in all your components in the condition that you received them in. So we don't want to be putting any kind of glue on. Try and use hardware instead. Set screws are good for coupling motors, for example. So one thing people sometimes struggle with is joining corners. If you're joining corners at a right angle, it's always good to use corner clamps, which we have plenty of in the lab, and then machinist squares, which we also have a lot of. So this is an example of how they would be used. It's used to hold your materials at a right angle while you're putting the screws in. And then the image to the right shows all of the ways that you can support a right angle joint on wood. So you can cut an extra truss to support it. You can get some angle brackets like we have for the robot project. You can make your own brackets out of wood. Whatever you want to do, just keep that in mind. If you want your right angles to remain right angles, you're going to need to support them. So in the previous slide, maybe you noticed there were two different screws holding together that angle. So you need two fastening points to fasten things together so that they'll remain stationary. If you only use one fastening point instead of two, so only one screw, you end up with a pin joint that has rotational freedom. So this picture shows how these two pieces of wood are now links and the bolt going through it is a pin joint, so it can, either of the pieces of wood can rotate about that pin joint. This is a pretty useful idea if you want to use this. Pretty much some bolt washers, a nut, and then they used a bushing or a sleeve bearing, probably made of plastic, to go through the middle. Just because metal and wood don't have great coefficient of friction against each other, this joint would probably be a little tight if they didn't use the plastic to reduce the friction. Some other ways that you can use joints to get the motion that you want to is by enforcing constraints on them. So the first way is rotational constraints. You can use things like hinges, a rotating Lazy Susan, and then like a pillow block bearing. That's the turquoise one. That's earlier. Those are really expensive, not in your budget, but it's an example. And then over to the right with the black flanges, that's the sleeve bearing, which is what I was talking about earlier. No part of that is actually moving. It's just plastic on the inside, as you can see. So it allows a low coefficient of friction, so you can have a shaft or an axle spinning in that hole pretty freely. And then instead of rotational constraints, you can also have translational constraints. So that would be a drawer slider or a linear bearing, which are the bottom two. Drawer slides are very common in this class. I'm sure you've seen them. It's a little hard to find linear bearings at a low price, which is why you don't see that as often, although they do. They look very good aesthetically, and they have some interesting mounting capabilities. Up next, I just have some tips for 2110 and how to be successful. So the first one is your robot is going to be made up of a bunch of mechanisms working together. If you think back to maybe high school physics class, you might have learned about the simple machines. This is something Archimedes came up with, and the 6 simple machines are just ways to gain a mechanical advantage in order to multiply a force. So the first one is a lever, then we have a wheel and axle, we have a pulley, an inclined plane, wedge, and a screw. If you think about it, you're probably going to end up using most of these in your 2110 robot, if not all of them. But yeah, these are all ways to exert some sort of force and end up with more force than you're exerting. Next, I just have a few tips for your robot design to help you be a little bit more successful, avoid some common errors. One issue that comes up often is wire management. So it's very easy for loose wires, such as the wires coming off of your mechatronics components, to catch on bolt heads, screws, the ends of zip ties, or anything that's moving on your robot, which is probably going to be most of it. So in order to keep your wires all secured, you can use things like heat shrink, you can use zip ties, twist ties, even spiral covers for wires to help hold them together. This picture shows before and after of the same wiring panel, but with wire management. It looks like all they've done is use some zip ties, but it looks much better. It's much more manageable. Another good thing to do is use LED feedback. So you're going to have 2 LEDs on your board. You're also welcome to purchase more LEDs and wire them up to your Arduino if you know how or if you want to learn how. Just remember you need to use a resistor if you do that. So you can use those LEDs to indicate things about your robot, like the status or state of it, indicate a chosen protocol. So in the final competition, there are a couple of different ways that the track can be set up, and you're not going to know which configuration the track is in until you get there. So instead of having 3 different codes for the 3 different scenarios, you might want to just have one code that will work for all 3 of them, and maybe you use a button on one of your button inputs to choose to let the Arduino know which configuration you have, and then you can use the LEDs as indicators to ensure that the program is running correctly. Another one is sensors. You're not constrained to just the sensors in your mechatronics kit. So as long as you stay in budget, you can totally feel free to check out other sensors. Some ones that might be useful for you are maybe a different encoder, if you want to use an encoder for any kind of purpose, a light-sensitive diode, and then an ultrasonic rangefinder. People have definitely used the ultrasonic sensors in the past as kind of a replacement for the IR sensors. And then when you are wiring up your sensors, you should always check your solder joints before any sort of major competition. You don't want the reason you failed to be because you had a solder joint break. And then if you have any really critical joints, you should use heat shrink or electrical tape, as it does 2 things. It reduces the amount of strain on the wire if it gets like pulled on or stepped on, but then also if something does happen to come unsoldered, you always have the heat shrink or electrical tape that might hold it together if you get lucky. So the bottom picture shows how to use heat shrink to protect your wires. So here are just some common mistakes. TAs have been compiling these next 2 slides as a list over the past couple of years. So these are things we've been seeing come up for years and years. The first one is to not build without a plan. Some people will just buy some wood, buy some screws, come to the Idea Lab, and start trying to put things together. But this usually doesn't work very well for them. So as I said earlier, you should always make a CAD model first. When you're putting together your frame, sometimes they end up slanted or just not very sturdy. Your right angles are really not right angles. That may end up causing you trouble later on, especially as you start mounting things to the frame and adding more components. So it's always good to fix that up front. Remember that duct tape is not a fastener, and neither is hot glue, really. We don't ever want to see any duct tape or hot glue at design review. Another thing that you should do is to modify your mouse traps. You'll be provided with just some standard mouse traps. They're really useful because of the springs that come in them, but the rest of it is very, very weak wood and will break. So you'll see people not change out the wood part of their mousetrap, just leave it all as they got it, and that wood is going to end up cracking and falling apart. Another mistake that we see is overusing string, especially if you have some sort of pulley system. You don't want any more string than necessary. It's really easy to tangle and snag, especially with all the moving parts. You always want to regularly inspect and maintain your machine. The lifetimes on these machines are not very long at all, so you can definitely expect things to break even if you're not really doing anything wrong. So you want to check and make sure, try to avoid that if you can, especially before a competition. Another mistake that we see is in coupling and mounting motors and actuators. So we've seen people hot glue motor shafts to wheels, and surprisingly, that doesn't work very well. So like I've said many times, it's always best to draw something up in CAD, just make a quick little motor coupling and 3D print it out, or buy one on McMaster. That's much better than being lazy about it, because that'll come back to bite you later. Another mistake that we see often that is especially going to be a problem this semester is waiting until the last minute to use equipment. Especially now that we have the reservation system for printers and laser cutting, you can't just come in and use the machines whenever you want. You want to, of course, work ahead as much as you can. You also want to test multiple times in different conditions. So in the past, I've seen people test their robot one time on the track. It worked great. And they were like, okay, cool. We did it. And then they stop. And then they get to the competition in their section and it doesn't work. And that's because you really need a couple of test runs to make sure that no bugs are going to pop up, that it wasn't just a lucky break, that nothing bad happened. You also always want to test on different tracks, in different lighting conditions, pretty much anything that could affect your sensors. Different flooring, maybe. Another common mistake we'll see is design fixation, and I mentioned this a little bit earlier. You need to be willing to move back and forth between the different phases of the design process. So don't get stuck on a design just because you've already spent a lot of time on it. Another mistake that is easily avoidable is gears that don't mesh or a wrong gear ratio. So we'll see people 3D print gears, it takes 8 hours, and then those gears don't mesh. And then they get very, very discouraged from trying to fix it because it took so long. So with some of the resources I've given you, like the gear generator websites or the SolidWorks Gear Toolbox, you should be able to avoid all those problems happening up front. But since we're all going to use laser cutting to make gears instead of 3D printing, even if it's not perfect the first time, it shouldn't be a problem to just go make a couple more gears on the laser cutter. And then finally, one that I really like to address is that you should always consider the trade-offs. When is it worth it to purchase a component rather than designing and manufacturing it? So I've seen people try for hours to get their plastic motor coupling that they made to work. You can go on McMaster and buy a little motor coupling for like $5, and it comes with set screws and everything you can. Same with gears. If you are just really having a terrible time with gears, McMaster sells a bunch of gears made of plastic, $2 or $3 each, free shipping one day. You'd know that they're going to mesh. There's not going to be a problem with that. So you should always think about when is it a good move to buy something and when is it a good idea to spend time designing and making it. Of course, you have to take your budget into consideration when you do this. So in summary, what you're going to do in this class is use mechanisms and joining methods to make capable designs. Always remember your simple machines. You're going to use some adaptation of those in most parts of your robot. And then also, how can you constrain your mechanisms to do what you want with the joining methods? You want to select appropriate materials and prototyping methods. Make sure you choose the strategy that works for the strengths of your team. You want to plan and design your device thoroughly before you even start to build. So your design for manufacturing, design for assembly, a key component of those is CAD, as I've mentioned. Right, after this, I have an appendix and a couple of different resources that you can check out if you're looking at these slides online. I'm not going to go over them, but it has a couple more websites you can check out. It has some pictures of some previous competition winners showing what they did well. But that's all I have for this lecture. So thank you for watching and good luck with your robot.